So interpolation is one of the simplest and kind of obvious topics, obvious to the point that I think they are not very useful. But anyway, we'll go through the motions. Are you recording? Yes. Yes, I am recording. Thank you. So where do you use interpolation? You have done thermodynamics 1. You have referred to steam tables and ammonia tables and everything. Can you recall where you used interpolation when you were doing problems?
You have a value that was in between two values.
You have tabulated, say, for example, in the pressure column, you had 10.0 kPa and you had like 10.5 kPa, but you needed to work out what goes on at 10.25 kPa. So you use interpolation, right? You will try to do try to estimate if the x value deviates by a certain amount from the lower bound. So we'll call this lower limit and upper limit. And this value here, 10.25 minus 10 is 0.25 kPa. The question is, if the x value is 0.25 units above the lower limit, how much will be y value shift? Meaning, let me clarify a little bit. So suppose you have x1 equal to 10.00 and x2 equals 10.50, and your interest is to ask for an x value of 10.25, what is the corresponding y value? And say corresponding y values are, I'm just making up these numbers. So let's say this is 4.34 joules and y2 is 5.45 joules. So here you have a delta of 0.25 kPa. What will be the change in y? That is, if you define y minus y lower or y1, how much will it be? Before you tell me a number, tell me how would you think about this? Here you have x, say x1 and x2, and for x1 you have a corresponding y1, and for x2 you have a corresponding y2, and those numbers happen to be 10.00, 10.50, and 4.34, 5.45. How will you think about getting the value of y at an intermediate value of x, which is equal to 10.25? Yes?
You would generate a best fit line between your known points. So since we only have 2 points, it'll just be a linear interpolation. And then once you have your equation, you put plug in. You have known.
So you're saying you have two known points, draw a straight line between them, and then draw this up to here and read out whatever value of y this is.
Yeah.
Does everybody see it that way? It's straightforward enough. That is, if this is a linear, if this value is somewhere between x1 and x2, you would think along this line, y would have the same slope so that you can easily back out what y should be. So now go ahead, assume that x1, y1, x2, y2 are known. Derive an equation for y, where given a value of x, what is the value of y? Okay, go ahead and derive it. What is the value of, or what is the expression for y?
4.895.
No, I didn't ask the number, I asked for the expression. How, I mean, if you understood this expression, you can do as many problems as you want. So let's, I want you to say, if you have this to be x comma y, how do you express y in terms of x? In fact, if you are doing this as linear interpolation, if this is halfway, your y should be halfway between the two. It's easy enough to say, but how do you write it as an equation?
That's gonna be y1 plus. Point of a fraction in the numerator, it's going to be.
Can you write it as y1? So if you are here, how do you identify a point along this line? This is like writing y1 plus slope times delta x. Right? If you want to travel along this line, you multiply by the slope and the distance you want to go. Simple trigonometry. So if this is delta x, this must be delta y. Right? That's what this is. And what is the slope? Slope is y2 minus y1 divided by x2 minus x1. Right? y2 minus y1 divided by x2 minus x1. And delta x is the destination that you want to go minus your reference point. Absolutely, your answer was correct, not the point of discussion here. What I want you to think about is, how do you remember these kind of equations without remembering them or memorizing them? How do you think about them? Here's your starting point. The concept is starting point plus the rate or the direction in which you're going multiplied by the distance traveled. Then what is the expression for the slope? And how do you think about the distance traveled, which is, if this is your starting point, it's the value of x minus your starting point, which is x minus x1. So put these two together, y of x equal to y1 plus y2 minus y1 divided by x2 minus x1 multiplied by x minus x1. So this is your formula for linear interpolation. This is in section 18.1. So congratulations, you just finished reading about section 18.1 in like 5 minutes. And if you are good with proportions, you can almost use that proportional knowledge to say, if you go 1/3 of the way in the x direction multiplied by the slope, you can almost say how far you will go in the y direction. And this is something you have done in your thermodynamics class, maybe even your machine design classes or mechanics of materials classes. So that equation I have there, it is equation 18.2 from the text. Equation 18.2. Okay, so you've done, you can write it up. And if you come back to this problem, what should be your value of y at x equal to 10.25? That is like writing 4.34, which is y1, plus the slope, which is 5.45 minus 4.34, divided by x values are 10.50 minus 10.00. And remember the units are joules per kilopascal. So this is like joules plus joules per kilopascal. So whatever you multiply this quantity with, what should be the unit of that quantity? If you are multiplying this slope, joules per kilopascal with a delta x, that delta x should have what units?
Kilopascal.
Should have units of kilopascal, so that the final unit comes out with joules. So what is the difference? 10.25 minus 10.00 kilopascal.
I got 4.895.
4.895 joules. That is your y value at 10.25 kilopascal. Simple enough. You're done writing. Now time to think and answer some questions. What is the problem in doing this approach in general? Or what is the, or when is the situation where you can actually use this approach and get good accuracy? And which are situations in which this is actually will lead to problems?
But this always assumes it's linear.
Say it again.
This always assumes it's linear.
It assumes it linear. Of course, that's the assumption. When is that assumption okay? Yes.
Over a very small difference.
Over a very small difference, as long as your interval is small enough such that any kind of change in curvature is not significant, and any slope can be reasonably thought to be a linear slope, or you can linearize the slope. So when to apply or when to use for reasonably small delta x or intervals within which the variation of y may be approximated as linear, and that's not a bad approximation. Whenever this is when the intervals are small or finely spaced. There are two possible scenarios where that might not be true. One possible scenario is if your interval is too wide, then a linear fit might not be a good approximation. That's one possibility. The other is there are some functions which are varying too fast that you can't call them as linear even in a very small interval. I'll give you one example. Try to take the function exponent of x and see what happens to the function. Say for example, if you think about exponent of x as a function of x, at x equal to 0, this is 1. What happens at x equals 1? It has a value of e. What is e power 1? That's like 2.716 something, right? So from 1, it jumps to 2.71. And what is e squared?
Like 7.389.
So e squared is 7.389. E cubed
20.09.
20.09, and you can see where this is going, e power 4, e power 5, and so on. So here's my question. If you take a delta x value of, say, for example, 0.25, between 0 to 1, delta x equal to 0.25 leads to the change in the exponential function. Say, for example, if you think e power 0.25 minus e power 0, what is this number versus between say 10 to 11, where same delta x 0.25, what is the change in the function? E power 10.25 minus e power 10. Can you compute these two differences and tell me? No need to write anything. I'll give you time, I promise. Answer these questions for me. What is this and what is this?
So your x's are 1.25.
Your x's are 0.25 and 0, 10.25 and 10.
For the first one, I got 0.284.
Okay. Second,
6,256.
say that please. 6,000.
6,256.
6,256. Yeah, that actually came out perfect to make my point, which is same delta x. Look at how much your delta y is changing in the two cases. So those at the back, are you able to see this? Do you want me to rewrite it? I can rewrite it somewhere else. You're okay? All right. Somebody interpret this for me. Same delta x. I'm drawing the curve like this. Between 0 to 1, I'm considering 0 and 0.25, and between 10 and 11, I'm considering 10.25. Can somebody interpret this for me, please? Let me rephrase the question. Hopefully, maybe I didn't communicate it clearly. I have x e power x, and I'm going to draw this like this. And let's say this is between 0 and 0.25, and somewhere else I have between 10.25 and 10. This is delta e power x. This is delta e power x. In this case, this is 0.284, and in this case, this is 6,256. Can somebody describe what's going on here?
You mean like why is one is so much different than the other in terms of difference?
Describe whatever comes to your mind. I want to hear people talk.
It's exponential function, so the difference between 0 and 0.25 is much smaller than 10 and 10.25.
Okay, I'll take that. Do you want to say something?
The slope of the function increases at a very fast rate. So between 0 and 0.5, the slope is changing slow enough to where it doesn't make that much of a difference for linear interpolation. But when you're at 10 and 10.25, the slope is changing extremely. So using linear interpolation results in a lot of inaccuracy.
We haven't gone that far yet, but what you said will be seen. But I'm looking at something like saying, suppose I told you that this is the function e power x is, I told you that. But instead of me telling you that, if you were just given a table of data, okay, xy values 0.00, 0.10, 0.20, 0.30, up to like maybe say 20, and you just have the table of values with you. Now, if you are given the task of reading out a value for say y at an x value of 0.25 and y at an x value of 10.25, you would beautifully do the same using the same formula. The only problem is when you did this first case with x equals 0.25 from the table, your answer would not be that bad. But when you actually do this with the 10.25 value, think about it like this. Here's your slope at this point. Okay, what is the slope? So I'm going to ask you, what is the slope of e power x at x equals 10? X equals 10.00. Your calculus 1 question. How do you get the slope at a point?
Well, that's just e to the 10th.
That is just the derivative of e power x, and you substitute x equals 10.00. And what is the slope here? E power 10. Can you tell me the value? What is e power 10?
22,026.
22,026. Okay. What is the slope at? What is the slope at e power 10.25? Just 2.25 units later, what is the slope?
28,282.
28,282. Thank you. So now, if you draw the slope 1 like this is 22,000, and then here it's already gotten much steeper. This is about 28,000. With this information and this equation, can you put together one sentence that tells me when I should not use linear interpolation? This fact, it changes very rapidly from 22,000 to 28,000 over the span of a relatively small interval. And this fact or this equation, which assumes constant slope between 2 points. Can you put these two facts together and tell me one sentence? Yes.
If we spot a change in order of
Louder, please.
if we spot the change in order of magnitude in our y values for a constant change in our x values, then we cannot use this method.
Can you try saying the same thing, but try again, little more accurately? You're kind of in the ballpark.
If we see a proportional change in delta x that's constant between the different values, and we see the change in order of magnitude in our different y values, then we cannot use linear interpolation.
You can still say the same thing with fewer words, which you're missing one important word. That's what I'm looking for. Yes.
With a rapidly increasing slope over a short distance, you should not use linear interpolation.
There is, when you say, why should the slope only increase? Why can't the slope decrease?
Or rapidly changing.
Rapidly changing. So if you have 2 points, okay, this model here assumes the trend line between them is linear, meaning you have broken down the interval to such a fine level that anything will look linear. But for the same 0.25 units, this function is such that it won't look linear, because that's the nature of the function. It's about the function that it rapidly changes. So if you have a tabulation, one thing you can always do is you can fit your function, right? You just learned about curve fitting. You can fit your function that is in the data, fit a function to your data, and use that fit itself to inform which type of interpolation model to use. Okay, so if your interval is fine and if your function is sort of well behaved, and by well behaved, what I mean is it increases, but increases in more or less like a controlled way, then it's okay to use linear interpolation. But if you have functions like exponents, can you name one other function whose slope abruptly changes or changes rapidly? Louder, please.
Say logarithmic functions.
Logarithmic functions, nice. So how does a graph of a logarithmic function look like? Ln of x, or if you want, I can write ln of 1 plus x. When x is 0, ln of 1 plus x is 0. When x is infinity, it just grows to infinity. Right? Any other, and even in this, the slope actually increases rapidly for some time, and then becomes the increase is not that high. Any other function whose slopes grow very rapidly or change very rapidly? Think trigonometry.
I'm gonna say any polynomial of higher power.
No. Polynomials usually, if you take any polynomial of this form, ai x power I, where I equal to say 0 to m, The nature of polynomials is that as long as these constants are finite, there is always an interval in which they will grow slowly. So polynomials can almost always be used with linear interpolation if you choose your interval to be fine enough. But there are some functions, they are just constructed that way that the moment you see them appearing in your data, you should think twice about using linear interpolation. Exponential function is one such. What's the big deal about this? We had this COVID pandemic, right? Why do we always start with the news story always starts with 10 persons had this disease. They entered in New York airport and they were quarantined, but eventually it goes into the entire country. Why do you think that's the case? Because any kind of infections, they spread exponentially. Initially the rates are low, but after a while, as more people are infected, the number of infections grow that much faster. Okay, so exponents are one such. One more example I want. Trigonometry.
Tangent function.
Tangent function, nice. So how does the tangent function look like? So 0, pi by 2, minus pi by 2. Tangent of x is 0 when x is 0. It becomes infinity when x goes to pi by 2. It goes to minus infinity when x goes to minus pi by 2. And what happens in the next interval?
It restarts essentially.
It flips. This is an enormous change in slope value. That is, you had a positive slope in this instant, and suddenly you are having a negative slope. No, the slope is the same, but the slope changes from positive, it goes to 0, and then it curves up again. So the slope is rapidly changing depending on whether you are here or whether you are here. Yes.
Would we also care for mention sine and cosine functions for that? Or do we just
Sine and cosine functions are more better well behaved. So this is your sine function. This is your cosine function. You can always chop them down into small intervals such that they look linear in that interval. When you are presented a table of data, right away, do you know what function describes the data? You don't. You start with this information. Next, what is the next logical next step? Graph it. Take a inspection of the graph. You will immediately see if it's a polynomial or linear or exponential and so on. Once you have that information, then you select your interpolation function. If you blindly use linear interpolation for any function, any data set, you will end up with these kind of situations. Okay? That makes sense? You can't just take and apply linear fit for every situation. That's the point. Suppose you have a function that here is 0.1 and here is 0.2, very far away, and within that point it does something like this. That is, the underlying function is doing this, but if you take 2 points that are so far away that within them there could be a maxima or some kind of trend or change in the curvature, applying linear interpolation here, between x1 and x2 in this situation is incorrect, is inappropriate, because by doing that you are missing a great change in the trend. That is, you would read, suppose your x value is here, you would read this as your y, whereas the true y is here. That's the problem. So how do you solve this problem?
If you have more points, then you can try to fit a better curve.
You can do that. That is, instead of fitting only linear, we can fit a second order or a third order curves. In practice, that is the most common thing you will try to do is try to increase the resolution of your data tables, or you will try to not apply linear between this, maybe apply linear only between a shorter interval. That's sort of like a practical fix. But coming to what you said, if you had more data points, that is instead of this x2 being here, suppose you had x2 here and then x3 here, you can take a template that involves 3 points and fit a second order curve. To fit a linear curve, how many points do you need? Yeah, exactly 2. If you have 2 points, a template that involves 1 and 2, you can fit a linear curve. You can't fit anything else. If your template involves 3 points, you can fit a second order curve. So you can write y equal to a0 plus a1x plus a2 x squared, and you know x1 y1 x2 y2 x3 y3. You can figure out what a0 a1 a2 are, right? How will you do that? Don't think about curve fitting. This is not curve fitting. This is trying to pass like a, suppose you have like 3 pins. It's like trying to pass a thread that goes around 3 pins. Okay, so how will you do that? 3 data points, 3 coefficients that need to be solved for. So substitute x1 y1 y3 equal to a0 plus a1 x3 plus a2 x3 squared. Treat a0 a1 a2 like unknowns and solve for them. So this is a 3-point template. 3-point template. Okay, we'll do examples. Okay, I'm just giving you the concept first. This would be a 2-point template. 2-point template. So if you want to fit a cubic curve, how many points will you need to involve? Cubic curve. You already involved 3 points for the second order curve. You want to do a cubic. So you have to involve 4 points. So your template expands to now 4. So we are going to do an example where I'll give you a data set. First, we'll fit a linear interpolation curve. Then we'll fit a second order interpolation curve and see how the process is different. But they all lead to the same end goal, which is what? Which is to evaluate the function at points which are not included part of your original data set. That's what interpolation is about, right? So let's try it as an example. Hopefully it will make sense. Before we go, any questions or any comments, anything not clear that you want me to repeat? Yeah. Was there any question? Sorry. All right. Problem 18.5 from the textbook, page 524. Problem 18.5, page 524. So you're going to fit a straight line, or you're going to use linear interpolation to calculate values of the function at the points that I'm going to tell you, okay? So given the table here, problem 18.5, let's calculate the function value at 2.8. There is 2, there is 2.5, there is 3.2, but not 2.8. First, let's use linear interpolation to calculate the value of the function at 2.8. So, iteration 1, we are going to use linear interpolation, which involves a 2-point template. And in our case, we want to calculate f at x equals 2.8, where x or 2.8 falls between 2.5 and 3.2. So our x1 is 2.5, x2 is 3.2, y1 or function at x1 is what? 14, and function at x2 is 15. So if I want to do linear interpolation, for those who can't remember or those who want to remember it conceptually, f of x equal to f of x1 plus slope times delta x. Step 1. That is, if you write it like this, x1, x2, y1, y2. And here is my line. So if I start here, if I write this is delta x, what is this distance? That is slope times delta x. Slope equal to m. And what is the slope? Slope is simply the, if you draw a triangle between this x1 and x2, y1 and y2, this is y2 minus y1 divided by x2 minus x1. And delta x is x minus x1. So now, put in the values. What is f of x1? 14. What is the slope? 15 minus 14 divided by 3.2 minus 2.5 multiplied by what is delta x? 2.8 minus 2.5. There is 14 plus 1 divided by 0.7 multiplied by 0.3. How much is that?
14.
14 point?
14.33.
14.33.
No, just leave it, just 130. So just 14.3.
Wait, 3 over 7 is not exact.
I got 14.43.
Yeah.
Okay.
Should be 14.42. Yeah, I wanted to 4 decimal points.
4286.
Thank you. 14.4286.
Another question.
Yeah.
Why didn't you just take the difference between the two of those and then you could make a fraction so that we wouldn't have that string number multiplied into it. Or do it that way?
I mean, you can do arithmetic in many ways. This is 1, 3.2 minus 2.5, 2.2 minus 2.5, 3/7. Is everybody able to do this calculation? Right? In these type of mathematics textbooks, you will see the word slope being used. In real life, especially in measurement scenarios, the change in the dependent variable for a given change in the independent variable is often called sensitivity. You can use the word itself as a clue to what it means. It simply means when you change a certain input, how much does the output change? So when I walked in, I was told that the temperature was previously 76. If you change the temperature by 1 Fahrenheit from 70 to 71, I wouldn't know. 71 to 72, I might start to notice, but beyond 72, I will definitely know. So like the sensitivity range, if it's like 3 Fahrenheit change, I can definitely have some change in me. Some physiological response that I'm telling you. In general, whenever you have some quantity, what you should think about is when you're doing an experiment, say for example, you're designing an experiment in which you want to measure the drag on some airplane model and you want to vary the wind speed in your wind tunnel from say 1 meter per second to 10 meter per second. Immediately the question in your mind should be, what is the sensitivity of my drag force to this velocity change, assuming everything else remains fixed? So how would you estimate that sensitivity? If suppose you have a measurement apparatus, you can slip in your airplane model, run the pump at say 1 meter per second, make a quick measurement, and then do the same at 10 meter per second. You can calculate what is the change in my drag force divided by the change in my velocity, and when would you call this experiment as being very sensitive to the velocity?
When it's slower. Would it be when I said slower?
You calculate this ratio, change in the drag force divided by the change in the velocity over which you are doing your experiment. When do you think this is a very sensitive experiment to do? I'll give you a binary choice. Is it a sensitive experiment when this ratio is 0, or in other words, drag is not changing much with velocity, or is it a sensitive experiment when this ratio is actually a high number, some kind of high number?
High number.
It has to be a high number. There is this. If you are varying an independent variable, there has to be a change in the output. If there is no change in the output, why bother do the experiment? Right? So this term sensitivity is very powerful. Whenever you look at data, it is essentially telling you what your sensitivity is. If your graph looks like this, that means the parameter y has no relation with x. That's what it means, like a flat line. If it looks like this, it's linearly sensitive. If it looks like this, it is exponentially sensitive. So in addition to learning this method, I want you to learn the significance of this word sensitivity, which you will encounter in your laboratory courses or whenever you are doing design of experiments. Okay, how to select parameter. Suppose you find out that in this range the drag doesn't change much with velocity. What is your judgment in the next step? I'll rephrase the question this way. Suppose you are interested in the range of 1 to 100 meters per second of velocity. In terms of doing the experiment, 1 to 100 meters per second is a huge range because getting airflow at 100 meters per second is a lot of work. You have to have a big enough pump, you have to have the duct system, you have to have a filter to remove the dust particles, all the things. So if you give this task to me, first thing I'll try to do is divide this into ranges and try to see which are the ranges in which nothing interesting is happening. So I will split this into say 1 to 10 or maybe and then say 10 to 100. Suppose, for example, my velocity and my drag force have this kind of a relationship. I know it is sort of flat here. Why bother doing a lot of data points where nothing is happening? So I would try to space out more points here than here. So I'm not going to be in the exam hall trying to tell you for a given data set, which will give you the best accuracy. I'll kind of leave it open-ended to say, use a suitable order polynomial for interpolation and get me an answer. I'll be looking out for the answer, and your choice for interpolating polynomial and the accuracy you obtain, those are all your decisions, which you will judge. That makes sense? So you have to think about sensitivity more than what just linear fitting or quadratic fitting. It has to capture how fast is your data varying with respect to x. Okay. So now let's repeat this problem with a quadratic or second order curve. How would you do that?
To make your three equations. Or are you doing the second order?
Second order.
Then you need to make your three equations using your three different functions that you have.
So before we do that, can I erase it? Is everybody done writing? Good. Everyone's okay? All right. So now we want to do quadratic, which obviously means we are going to use a 3-point template. So quadratic interpolation, 3-point template. Okay. So the picture changes. I still want to compute what is f of 2.8. Okay, so there are two ways to do this. You can think of 2.8 as lying between 2 and 3.2 or between 2.5 and 4. Do you see that? It can involve these 3 points, 2, 2.5 and 3.2, or 2.5, 3.2 and 4. There are no other choices. You can place the stencil here or here. So I want the class to split into 2 groups. One group will use stencil 1 and the other group will use stencil 2. Okay, let's get 2 answers. So maybe everyone to the left of this use the first stencil, and everyone to the right of this use the second stencil. Yeah, maybe you belong to that. So f of 2.8. So I'm going to write x1, x2, and x3. Okay. So I'm going to fit something like this. So stencil 1, we have x1 equal to 2, x2 equal to 2.5, and x3 equal to 3.2. And stencil 2, x1 equal to 2.5, x2 equal to 3.2, x3 equal to 4. Corresponding f of x1, 8, 14, 15. F of x1 is 14, f of x2 is 15, f of x3 is 8. Is anyone not clear how to get started? You want some help? Speak up, please. So our template is like this: f of x equal to a naught plus a1x plus a2x squared. Use the x comma f of x values at 3 points, that is the 3-point template, at 3 points to set up 3 equations in 3 unknowns. Once you set it up, since you are already familiar with solving linear equations, you can figure out what A0, A1, A2 are from the data. To increase my board space, I'm going to write on Zoom. Okay, so I have f of x equal to a0 plus a1x plus a2 x squared. Can the stencil 1 people tell me the equations to use? First equation.
8 equals A naught plus A1 2 plus A2.
A1 times 2 plus what is A2, like x squared?
A2 to X squared.
4A2, right? X equals 2, isn't it?
Yeah.
Yeah. So this is x equals 2. And then x equals 2.5. And then x equals 3.2. So when x is 2.5, what is f of x? 14, right? 14 equal to a0 plus 2.5 times a1 plus what is 2.5 squared? 6.25. Thank you. 6.25 a2. And then f of 3.2 is 15. 15 equal to a0 plus 3.2 times a1 plus what is 3.2 squared?
10.24.
1024. Thank you. 10.24 a2. Now solve for a0, a1, a2. Now my other group, stencil 2, your x values are 2.5, 3.2, and 4. And since we go second, you can copy these two equations and put it as equations 1 and 2 on your column, because it's the same data points. So same as here. And for x equals 4, what is f of x? 8. Is it 8? Yeah, 8. 8 equals a0 plus 4a1 plus 16 a2. Only caution is these a0, a1, a2 values are specific to stencil 1 and these values are specific to stencil 2. If that is not clear to you, maybe use different symbols to keep it separate, but this is a completely independent calculation as this. Think of it like a parallel universe. Okay, this is separate, this is separate. These are two independent ways of doing the same calculation. Group 2 people, do you have any doubts? Like I just use the same symbols, but they mean different things. I hope that's clear.
Once we get the, once we get the A0, A1, and A2 values.
For stencil, your group two.
No, for the two different ones.
Yeah.
How do we choose which one we prefer to use?
Do both. We'll answer that question at the end. So group one people, anyone has values for A0, A1, A2? Same with group two. Yeah.
How many decimal places do you want?
3 or 4.
3 or 4?
Yeah.
All right, A naught is negative 60
Your group two,
group one,
group one. Yeah, okay. A0 is
negative 60.0476.
okay, 60.0476. And A1 is
51.6429.
6429. And A2 is
Negative 8.8095.
okay. Anybody from group one or group two? Yeah. Your group
Oh, yeah.
one.
Group two, A0, negative 43.8571.
Negative 43.8571. And A1 is
40.1071.
40.1071. And A2 is
Negative 6.78.
okay, good. So we have the values for the coefficients with both the templates. Now using both the templates, I want you to compute what is f of 2.8 using the first set of coefficients and also with the second set of coefficients.
Not 153 and 13
153.
for the two. So.
Can you more decimal points? Yeah.
153.6190.
6190 and
The other one we got 13.2429.
you have different values for both the estimates.
First estimate, about 15.4859.
15.4859.
Or 4860, sorry.
4860. Okay, and for the second stencil, anyone with the value for the second stencil? 15.2429. All right, now I'll give you time to catch up to write 2 minutes. Once you're caught up, we are going to talk. This is time for you to catch up on the writing. Please finish it and then drop your pens. So to summarize, what have we done so far? We were presented a table of data. We wanted to get the function value at 2.8, which was not part of the data. 2.8 can be thought as between 2 and 3.2 in this second interval, or it can also be thought as between 2.5 and 3.2 in the first interval. And when I say 3-point stencil, what I'm really talking about is this. You have, say, 2, 2.5, and 3.2. There are 3 values of x. So what is the first value is 8, second value is 14, and third value is 15. So the curve would look like this. Listen, please. You can talk. You can write later. You have three points that look like this, and then we figured out if it is 2.8. It has to lie somewhere here. Lie somewhere here. Now, what was the value we got? We got 15.4860. 15.4860 or 15.24. So what you can readily notice is that practically these two values are similar. The choice of stencil 1 or 2 is not a deal breaker in terms of the accuracy. Okay, so if you choose either method and do it correctly, you will get equivalent answers. Okay, because at the end of the day, you're doing a estimation or kind of a approximation of the data, which both of which are reasonable. So in one case, I've drawn this diagram wrong. In one case, 2, 2.5, 3.2 is your stencil, and the other case you have 4 included, and these 3 are your stencil. So you have 2 of them. Okay, so it's like then fitting a curve with 3 points, because the third point is like 8. The drawing skills don't save me when I need it, but anyway. So this is the third stencil, which looks like this. So answer this question for me. If you are to write a computer program which has to do interpolation according to second order or third order or fourth order polynomial, what are the inputs to that program and what will be the output of that program? If you are using a quadratic interpolation, how many inputs do you need?
You need 3 points and then 1 point which you're trying to find.
You need 3 points, that is 3 pairs of data,
And then 1 other x value which you're trying to find.
and then an x value, which is the input. And if you feed this to your program, what will be the output of your calculation?
Here, 1 value.
That's fine. I know you are getting this, which is good. Let's give others a chance. So if you do that calculation, what is the output to your output from your code or your program? Sorry?
Shouldn't it just have a best output?
It should be the value of f or the function at the x value desired. Is everybody seeing this? And in the next 10 minutes, can you write this as a MATLAB program? No. But my point being, once you select the template or the stencil, which could be a linear or a quadratic or a third order or fourth order curve, how many parameters do you need to solve for, or how many data points do you need to do the fitting? If it's linear, how many data points do you need? 2. If it's quadratic, always 1 more than the degree of the polynomial. Cubic, 4, and so on. So if you are thinking about a data set, for example, let me bring back that if you are thinking about a data set, for a moment, forget the last and first and last data point. You can apply quadratic interpolation for any of the ones that are second, third, fourth, or fifth, not the first or last. Why?
Because no data point on the opposite side of the first and the last, I'm not sure.
Be- Because if you're trying to do, if you're trying to say apply quadratic interpolation between 2 and 8, sorry, 1.6 and 2, you can do only one stencil which is quadratic. It can only involve 1.62 and 2.5. There is nothing to the left of 1.6. So one of the stencils is not available to you. If you are doing the last data point and say you want to figure out what happens at 4.25, your stencil can be 3.2, 4 and 4.5, but not anything larger. So there is only one stencil choice for the first and last data point. For the remaining three, there are two choices of stencils. Does that make sense to you? If you are doing linear, is there any change between the first and last data point? That is, if you want to do 1.8 or 4.3, would the methodology be any different than doing 2 and 2.5 or 2.5 and 3.2? No, right? So linear is by far the simplest. There is no specific attention that you have to pay. Quadratic is a little more complicated. What about cubic? Answer this question for me. Which are sort of the boundary points in which the number of stencils are restricted when you're doing cubic interpolation? What about 2.5? Which are the ones you will pick as stencil? So suppose I want to do 2.8, same 2.8. Can you pick out stencils for cubic polynomial? 2.5, 3.2, 4, 4.5. That is one possible stencil. We can also do 1.6, 2, 2.5 and 3.2. That's another possible stencil. What is the requirement? The stencil should contain your value. You could also, that's the third choice. Now there is also a third choice, 2, 2.5, 3.2, 4. It falls in the middle. So you can now have three choices for your stencil for cubic fitting. Suppose I want to do 1.8 for cubic fitting. What is my stencil? Or what should be my stencil? 1.8, x equals 1.8. How will you pick a cubic polynomial stencil?
That's the first four.
I am also going to ask you to kind of give others a chance. So let's hear from other people. I want to get x equals 1.8. What is the stencil anyone will pick? I want some responses.
1.6 to 2.5.
1.6 to 2.5, 3.2. Can you pick any other stencil? There is no other possibility. What about if you want to have a value at 2.25, how many stencil choices are there?
Two.
Which are them?
Yeah, 1.6, 2, 2.5, 3.2, 2, 2.5, 3.24.
Two choices, only two choices, as opposed to 2.8 where you had three choices. So what you should start understanding is there is a difference between boundary versus interior. So when you do linear interpolation, there is no boundary points. All points are treated similarly. When you do quadratic interpolation, which are your boundary points? The first and last, because they behave differently. When you do cubic interpolation, which are your boundary points? Or which ones have to be treated differently? The first and second, last and last but one, because the stencils change. Anything in here will have three choices, whereas these two and these two will have only two choices. In fact, this has two choices, this has only one choice. So let me write it out here. So I'm going to write my table x, f of x, 1.6, 2, 2.5, 3.2, 4, 4.5, 2, 8, 14, 15, 8, 2. So I'm going to do linear interpolation. Linear interpolation for any interval, say for this interval, there is only one choice of stencil. Right? Any interval has only one choice. That is when I put this, what I mean is if I want 2.8 which lies in this interval, there is only one choice for the stencil, which is these 4 points. One choice. One choice. When I do quadratic interpolation, if I want to pick 2.8, how many choices of stencil are there? For 2.8, this is a valid choice, and so is this. Right? So can I write two choices? Everyone's cool with that? If I were to pick anything between 3.2 and 4, suppose I want say 3.6, what are my choices? Either these three or these three. How many choices? 2. You're dozing off, wake up, this might show up in the exam. Okay? If I have say 4.2 here, how many choices? How many choices of templates or stencils? I can pick 3.2, 4, 4.5. Can I pick anything else? One choice. And if it's between 2 and 2.5, say suppose it's 2.3, how many choices? 2. 2. I can pick these 3, or I can pick these 3. That's 2 choices. And at the end, if I have say 1.8, how many choices? 1. Just 1. I can only pick these 3, nothing else. You will see a pattern here. 1, 2 to 1. Whatever has only one choice, we'll call it, or whatever has 2 choices, we'll call it interior. And whatever has only one choice, we'll call it boundary. That is with respect to, that is for only quadratic. So whatever has 2 choices is interior, and anything that has only one choice is boundary. And if you do a cubic polynomial, first of all, in a cubic polynomial, how many parameters you need to solve for? 4. 3 plus 1. A0 plus A1x plus A2x squared plus A3x cubed. That's 4 parameters right there. Right? Okay. So 2.8, how many choices of templates do we have? Which 4 points can we choose if you are interested in 2.8? So if I want 2.8, I can do it as 2.5, 3.2, 4 and 4.5. What else can I do? 2, 2.5, 3.2, 4, 1.6, 2, 2.5, 3.2. Is there any other choice? No. So I have 3 choices. So for 2.8, I have 3 choices. What about 2.3? You have 1, 1.6, 2, 2.5, 3.2, 2, 2.5, 3.2, 4. That's it. Only 2 choices. And what about 3.6? tell me without counting. What about 3.6? Just by symmetry, it should be 2, right? And the last one, 1. Only one choice. Only one choice. So for cubic, anything that has 3 is called interior, and anything that has less than 3 are boundary points. Now, anyone, can you tell me, once you have identified a stencil, the next step? What is the next step after you identified a stencil? Set up either 3 equations or 4 equations and solve for the coefficients. Next question. The choice of template, if you are choosing the template, there are 3 choices or 2 choices or whatever. Does the choice of a particular template will influence the answer? Yes or no? That is, if you choose there are 2 choices, say choice 1 and choice 2, will you get different answers with different templates, different stencils? Yes. So you will get practically same answers. That is, nominally they are the same. 15.40, 15.21, it's not very hugely different. So in your exam, don't sweat over, is there a correct template to use or stencil to use? There isn't. If you did it logically, both of them will give you similar answers. So you and your friend who took different approaches will get almost the same answer. Okay. So this is covered in section 18.1 and 2. And what I want you to be able to do is take any table of data given in this set. Don't worry about the Newton formula or inverse interpolation. Those are things we didn't discuss. I want you to just use up to 3rd order polynomial and practice. Because in the exam, I might ask you any one of these. It's not a big deal for you because once you set up the equations, you are well equipped to solve for the coefficients. What we will be specifically looking for is how do you select the stencil? If you had a, say for example, 1.8, this is possible because I've seen it happen. The students have chosen a template that doesn't even include that point. That's a cardinal sin. If you are choosing a stencil, it should include the point you want the interpolation done at. Okay, so don't exclude it and then choose your template. That would be bad. And they might sometimes imagine or they might add their own data and do the calculation. Don't do such thing. For the given data, logically explain how you chose your stencil and then do the calculation. Okay. So that excuse me, that wraps up module 4. We will have the problem solving session at 1 o'clock, 1 to 1:50. And on Thursday, I will start the next module, module 4. Okay, I think it's numerical differentiation and integration. Homework has been posted. It's due the following Thursday. It's due October 19th when you come back from your fall break. Okay, it's just 4 problems. Please work on it. Do additional examples. One thing I really want to emphasize is in the homework, there are only 2 or 3 problems. It doesn't mean that that's enough for you to get competent. You need to do a lot of practice. Okay, so please see you at 1 o'clock.